All right, so for this class, for this lab, we'll actually start with GeoDa, and then if we have time, we can go to the notebook, but I don't think we'll be able to. But anyway, you'll see that the notebook pretty much replicates some of the things we can do in GeoDa, but not all of them due to the exercises we'll do with linking and brushing, and of course that we cannot do there. So GeoDa will be much more complete in this sense for what we're going to do now. So we'll use the same data set as in Luke's book. So the Italian banks data set, it is already part of GeoDa sample data. So we can just go straight away to GeoDa and load the data and start working from there. Okay. All right. So let's, from GeoDa, let's open the Italian banks data. So again, it's in the sample data tab and Italy community banks. So I'll just click here. And we already get the map. So it's a point data set, right? We have the location of each of the observations. So we have 261 observations in this data set and a lot of variables, which will complicate a little bit for us when we're running the methods because we'll have to select one by one. And since we're replicating the exercise, the illustration that is in the book, we'll use 10 different variables. But anyway, let me just skip this and we can start by visualizing at least part of the data that we'll use because I think it will be helpful for us to understand more the whole idea of the distance preserving methods that we will use today. So to begin with, as I said, we'll use 10 variables in the end, but before we move to 10 variables, let's just start with 3, because then it will be easy for us to just plot them in this cube. So if you can just click here on the 3D plot, or hate that whenever I try to use the menu, the zoom bar comes down. So yeah, let's just stay here. So just come to this 3D scatter plot of variables. And then scroll down all the way to this KPRAT 13. We'll start with it. So this is the ratio of capital over risk weighted assets. So for this 2013, right, Luke? The year of this 13. So we'll start with this one for the X. And then we'll use all the variables that are below this one, right? So, but again, now we'll just do 3, but for the remaining exercise, we'll use them all. But to begin with, select one of Z as well. So Z13 for Y. Z stands for Z-score of return on assets plus leverage over the standard deviation of ROA. And then for the Z-axis, we'll select the variable below. So as 13, which corresponds to ratio of liquid assets over total assets. Okay, so we'll just begin with these 3 variables and then hit OK. So we've been through these before, right? The 3D visualization of the data. And the reason why I wanted to show you this first and with only 3 dimensions, so we can actually have a better grasp of exactly what is going on with these methods, is that by looking into this cube, into this representation, we can see exactly within this 3-dimensional space, we can see how far the observations are from each other in this abstract space of the variables, right? So for example, we can see that we have some observations that are very far from the other ones, meaning that they have very different values for these 3 variables, whereas several of the observations are quite clustered, right, with very small values for all the variables that we're taking into account, right? They're very close to 0, 0 here to the origin. So we have a bunch of observations with similar values sort of clustered together in the orange of these 3 dimensions that we're considering. Okay, but since our focus is on spatial clustering, so our focus is on thinking not only about this abstract space of the variables, but also geographical space, we can check how these observations correlate these two dimensions, right? Variables and geographic space. So in order to be able to start thinking further about this, let's begin by creating one weights matrix so we can actually see for each of these points what are their geographical neighbors and how far they are from each other in terms of the variables as well. Okay, so I'll click here on the W from the menu bar, the weights manager option, tool actually, and then I'll hit create. And from here, we need to select an ID variable or just, create our own. Doesn't really matter, but we already have an ID variable here, IDD, so I'll just select it. And instead of creating a queen contiguity matrix, let's move to the other tab and already start with k-nearest neighbors, because then we'll reuse these for the comparisons that Luke showed about, checking like how many neighbors overlap or not and all of that, okay? So we can already begin and then it will save us one step afterwards. And here I'll choose 6 nearest neighbors. All right, again, please let me know if you want me to stop or if you need a bit more time. So what we're doing here is we are creating a weights matrix based on the 6 nearest neighbors. So GeoDa will assess the distance between each of the points in geographic space, right? Each of our observations. It will then rank them and select only the 6 shortest distances, and these observations will be deemed as neighbors for this matrix. So I'll just hit create. Now we need to save it. I'll save it on my labs folder. And now, since we're going to deal with several different weights matrices, it's important to give it a meaningful name, right? So I'll just call this, let's say, KNN6. Sorry. So I know it's K nearest neighbors with 6. And then I'll hit save. All right. And if we load now the connectivity map, or in this case, the graph we'll be able to see something. Let's open the connectivity graph. So it shows the observations that are being considered as neighbors in the geographic space, right? So here we have the geographic space, and here we have the abstract space of variables. Okay? So what I want you to do now is just to click on this option, select hold command for brushing. You can see that it creates this small red cube within the big cube where the variables are plotted, right, and the observations. By doing so, we can, by holding command, or I'm not sure what is the key in any Windows machine, but anyway, it should be control maybe or something like that. But anyway, we can move it. You can see I'm terrible at this, so I'm never able to actually pick up a point with just this small red cube. So I'll increase its size by just doing this.
This is actually not you, but remember the empty space problem?
Yes.
I talked about in the very beginning. That is exactly what this is. So there's a lot of empty space in between the points.
And I'll try it. Okay, I got it. Yeah. Whoa, I had to increase a lot the size of the thing. Let me see if I can. Yeah, anyway, I'm getting only one, so that's good. It's one fish and that's all I need. All right, so as you can see, if you look at the map here, so we have the unit that is selected, so the yellow dot here, right? With the edges connecting that unit to its neighbors in geographical space. So we are very close together in the map. But if we look at it here in the cube, right, in the 3D plot, they are very far from each other, right? So what is the idea? Here we have that when we're considering 3 variables, we have that these observations are very far from each other. And what the methods that we'll see today will try to do is to preserve this distance that here was seen in 3D But in the exercise, we'll be running it in 10D, right, in 10 different dimensions. The method will try to preserve these distances so that the length of the edge connecting these two balls, these two like dark yellow and brighter yellow balls, that this length remains as similar as possible in the end. Once we compress this data that now is 3D, later we'll do in 10D, when we compress it to 2 dimensions only. So we simplify it, we reduce the dimensions to 2 dimensions only, okay? And we'll do that right now. So I'll show you exactly like how you can visualize what is going on. But keep in mind that we'll start with this by just trying to preserve the distance between the points that we see in the abstract space, but decreasing the number of dimensions that we have in this data from 3D or 10D to 2D only. And then later, seeing how much this relates with this distance that we have in the geographic space. Sounds good? So this is the purpose of everything we'll do today. You want to ask something? It shows the, see these were selected already, show selection in the neighbors. And then once you created the weights matrix and you selected the select hold command for brushing, it starts selecting points. Since the weights matrix is loaded, once you select any point in this box, its neighbors will be highlighted. See? Does it make sense? So if you do not have a weights matrix created, it won't show you any of this because it doesn't know the neighborhood.
If you click on the map and you right-click on the map in the menu, right?
Oh.
Just right-click, you get the options. Yeah, if you see connectivity, you see show graph. So if you uncheck that, then you would not see the neighbors on the map.
Oh, you were asking about the map or the abstract space of the map? Oh, sorry. I thought you were asking about this. So the way I loaded this, I mean, Luke just showed one way, but the way I loaded this was from GeoDa's.
Yeah. If you load it from the
weights manager,
then it's checked automatically.
Yeah.
But for any other map, you can check this. By default, it's not checked, but you can check it, and then you can see the connection for the live weight matrix. So there's a slight difference. What Pedro showed is specific for the weights for which he clicked it.
Mm-hmm.
When you do it on any map, it's for whatever weights are live at that moment, which may be the same or may be a different. In this case, there's only one, so it doesn't make a difference. But if you have multiple weights, it does make sense to remember that on any regular map, it's always the live weights that are reflected in the connection.
All right, so let's decrease the dimensionality that we have in these 3D, on these 3 variables that we are using, and use MDS to do that. So let me see. So using this multidimensional scaling. So we'll go to clusters menu and then MDS. And now we can select the same 3 variables first. So this KPRED 13, Z, and liquid assets. Let's begin with the classic metric. So let's not change these. I'll show you later what happens when we do this MAC-off, like how to work with the category variable. But at this point, let's just use the defaults. Number of dimensions, let's stay with 2. And then, so let's just click run. So now we can save these new coordinates, right? We can save these new variables that we are creating from the combination of the 3 ones that we selected. So we can just keep these names, then we'll replace it once we do 10 variables. But this is the result that we get. So you can see here what is the stress value. So this is showing what is the absolute difference that we have between the distances from each point in the 3D space, right? All the variables in comparison to this reduced space, this embedded space where we have only two variables. And the rank correlation is, again, the correlation between these distances, right? From all variables, in this case, 3, when we compare it to 2 only. So Luke mentioned, but I'll just repeat it to make sure that you all understood it when he said it, that stress value and rank correlation does not necessarily go like side by side or hand by hand. And the whole idea is, for example, if you have that the distances between the points here are, let's say, twice as much for any reason as of the distances that we had in the 3D plot, the correlation would still be 1, right? If you multiply them all by 2. But the stress value would not, because the stress is just checking the differences that you have between the length of the edge that is connecting these points, okay? All right, so let's compare these two results and see what we have. So basically what we have now is a representation of the 3 original variables, so 3 dimensions. And here we have the same representation, the same 3 variables, but represented only in 2D, right? So it's the same 3 variables, but now reduced to 2 dimensions only. And once we have these side by side, we can again just, okay, something. Okay, let me decrease this so I can actually move from one window to the other. When we have all of this, we can again do as Luke said and right-click on the map in connectivity and then show graph again. Oh, sorry, show selection and neighbors. And if we find another point here, okay, let me try to get one again. Got it. So actually I should have selected the point first. I'll just go to connectivity and again uncheck that. And I'll check it again. So connectivity, show selection and neighbors. See? The difference is that now, once I already had someone selected, not sure if you can see much because the dots are so small here, but what we have is that we can see that these observations are clustered in the geographical space. It's the weights matrix that we created. You can see in this plot with the bright yellow dots, it's not a very nice selection, but anyway, you can see in this plot what is the distance between the observations that we selected and everybody else. And then you can see that there is no neighbor close to this point in the abstract space of variables, right? They are all far away. There is this one that is slightly closer, but still far. And then all the other neighbors are very far from the original point, but their distances to the original point is somewhat similar. Can you all see what I'm saying? Right? So now let's move to the 2D representation of this data. So again, the simplified one. And what we see is this was the original point, right? And then check its neighbors. So in 2D, we still have one point that is slightly closer. The other points are far away, but their distances to the original point is not that different when you compare all of them. There is only one apparently that is very far, and it's likely this observation here, right? It's the one that is farthest away from our selected our selected observation. So can you all see how we're just really compressing what we have in 3D, simplifying the whole dimensionality of our data, but again, preserving the distances that we have between these points when we think about their discrepancies in terms of the variables that we are considering, right? So we still have the very same pattern. If we are able to select any other, yeah, there's another one there that's slightly a better representation. Any other here, again, we have an isolate point there. So everybody is very far from it. if we go back to our 2D, see the point is very isolated there. Again, in the same way as it was with all variables, it is in the simplified version with 2 dimensions only. And if we again uncheck and check again the connectivity, it will show the neighbors of that point in the 2D representation. See? So now the neighbors are highlighted again, and we can see that the distance was preserved, right? That even though we simplified the data from 3D to 2D, we're still able to keep the same overall representation in terms of how far the points or how different these observations are from each other. Sounds good, the whole intuition? Of course, we don't want to do only 3D to 2D, right? Because that is not a huge gain in terms of simplification. So what we want to do is when we want to use this when we actually have some high dimensional issue with our data. So I'll close these windows. I'll come back to our MDS settings tool. And now let's get more variables into our analysis. So I already have 3 selected here. So the KPRAT 13, the Z, the liquid assets. And now I'll keep going with NPL. So NPL stands for a ratio of non-performing loans over total loans. And then double LP, which stands for ratio of loan loss provision over customer loans. Then Inter 13, so ratio of interest expense over total funds. Then Depot 13, so ratio of total deposits over total assets. Then EQLN 13, so a ratio of total equity over customer loans. Then XP 13, so ratio of operating expenses over total assets. And finally, the 10th variable, SERV 13th, net interest income over operating revenues. Okay, so 10 variables, right, that we've chosen from all the options that we have here. We'll keep, again, still the default. Let's just run this so we can see the result. So finally, again, variable names. We can give it a more meaningful name if you want, but I think V1 and V2 is fine. We're just doing the basic, right? The classic and all of that. So, okay. And here, finally, we have the 2D representation of the 10-dimensional space, right? Of the 10-dimensional complexity that we have from the variables that we selected. So again, the distance between these points will be as much as possible the same distance that we would have in a 10D representation, right? Considering all the variables. So summing up, getting the Euclidean distance between through all these 10 dimensions, roughly, we want to get the same distance here in this representation as well. So you can see that the stress value is of 0.39. So again, what we have here, what this means is that the difference between this distance in 2D and 10D, so we can use this number to compare for other applications, like how much this difference is. So we want it to be as low as possible. If it were, the distances were exactly the same, the stress value would be 0, right? If all the distances between the points, each of the points were exactly the same in 10D and in 2D, we would get the stress value of 0. And then the rank correlation is, again, just checking the distances that we have and seeing how much they correlate. So the length of these distances. And here is 0.8. So as Henok mentioned when he asked Luke about this, I mean, this is a high value, so it's a good result that we get in this application. All right. Does it make sense? So again, this still has nothing to do with geographical space, right? So we can get any 2 observations. Let me get these 2. Oh, I was lucky. Let me get other 2, because as you can see, these are very close in the in this the 2D representation, right, in the space of the variables, but they are also very close to each other in geographically terms. But yeah, finally, if you select at random any other two, you may get observations that are very far from each other, even though they show similar values, right? So again, we still are not checking the intersection between geography and variables at this point. What we can do now is compare what we have when we are using the MDS to decrease the dimensionality of our data and using the classic metric to what we would get if we were just running a PCA as we did last week, right? So if we come to clusters and PCA, we can do again the same thing, select, let's start with kpret, select the same 10 variables, so clusters, PCA, and then select all the variables one by one again. Oops, thank you. I wish they were ordered by year instead of by name. Since we want to compare, let's change the method here from a singular value decomposition to eigenvalue, right? Because the MDS is taking into account the eigenvalues and eigenvectors. Okay, I'm seeing some hands still selecting variables. I'll hit run. Here we have now the result of our PCA. So we have 10 variables, so we have 10 eigenvalues. They are sorted out. The Kaiser criterion is 3. The 95% threshold is 7. We are not going to interpret the PCA. We did this last week. All we want to do is save the results for first and second principal components so we can compare what we get from PCA to what we got from MDS. So I'll change these to 2, the output. So we want the first components, the first 2 components. And then I'll hit save. And I'll keep these variable names like PC1 and PC2. Okay. And now it's been saved to the table, the attributes table. So we can get back to our menu here and click on the scatter plot option, right? So we have the scatter plot option. And then for the x-axis, we can roll over until all the way to the end and choose PC1. And then for the y-axis, again, roll over all the way to the end and choose PC2. Yes. So when you have you click run first? Because the button for save will not be enabled unless you run it first. Did it work? Hannah, can you see if you can work? Because that's the thing, you can only save these 2 components after you run them. Everybody else good? Yeah. I mean, working now? Yeah. So if we click OK, thank you, Hannah. Yeah. Then we can see the scatter plots, compare both of them. And I mean, do you notice any similarity between them? It's pretty much the same thing, but mirrored, right? So it's flipped. What we have here is that V1, so the first dimension that we got from the MDS is exactly the same that we have as PC1, right? For the first principal component. But V2 It's again also the same thing as PC2, but with inverted signs, right? So it's flipped. Can you all see that now? That this is just flipped on the y-axis. So we have the same points, right? I mean, if we select them, here you can see that they'll be selected there as well. So, I mean, there's a way to, yeah. See, so they're just flipped, right, on the y-axis. So we have the exact same thing. We can actually, just to make sure that they are the same thing, we can create a scatter plot between these two, but before I'll do that, I'll just come back to the results from the PCA. So basically what we have is that since they are the same, the loadings for PC1 are basically what is being used to create also the first dimension of the MDS. Whereas here, if you multiply this by -1, you'll get the same idea for the second dimension of the MDS, right? So again, since we're still using eigenvalues and eigenvectors, and they are the same for both methods because it's the eigenvalues and eigenvectors, so the result that we get is pretty much the same thing. Let's try. Let me save. Then let's do the scatter plot, these new ones. Yeah, we get a similar but not the same result.
Pedro, can we think of this kind of PCA as a cheat to help us interpret MDS?
If you want to interpret the dimensions and you're using the classic metric, yes, you could look, because again, it's the same thing. Yeah. So you could, if you wanted to interpret this, you could come result to this.
But only for the classic.
Only for the classic, yeah. If you do this Markov, then the results will be different, so you cannot do it. Again, just to confirm, well, since we're already doing a lot of scatter plots, let's just come back here to the scatter plot function and do V1 against PC1. Hit OK. And then you can see we have an R squared of 1, right? So they are exactly the same in this case. And if you did V2 against PC2, in this case, you would get exactly a negative diagonal, right? Because it's just that the signs are different.
And MDS1 is always orthogonal to MDS2, just like PCA, same thing.
If you're using the classic metric, yeah. Okay. So since we're talking about classic metrics and this Markov and all of that, I'll just close everything about PCA, come back to the MDS window, and let's do it, right? So let's change from the classic metric to this Markov. So the big gain that we get from using Smakov in comparison to the classic metric is that the Smakov will use a different scaling, right? So the whole idea will to change the way the optimization is run, and then it does not depend exclusively on the Euclidean distances between the points. Because when we were doing the classic metric, we were minimizing the difference, the stress, right? So minimizing the differences that we got in the Euclidean distances between the points in the high dimensional space in comparison to the 2D, right? To the embedded space that we're creating. But with this Markov, we can do that either using the Euclidean distance or we can use the Manhattan distance, so we get more flexibility when we're running a different method, right? And so the whole idea here, when we run this Markov, we'll still do it with the Euclidean distance, but then we can see how it performs also with Manhattan distance and think about what makes more sense in our application or what actually yields better results. But you all know that the difference is that in the Euclidean distances, the difference between the lengths, right, or the distance between the points will be squared, whereas in the Manhattan distance, you'll be just summing up the absolute differences, right? So basically, this is what will yield different results. And then in the Euclidean distances, you tend to penalize more the outliers than when you're using Manhattan, that you're summing up everything. Okay, so let's sum here using this Markov. Let's run, sorry. And then I'll change the name. I'll just add an S. Where's Markov? And okay. And here's the result. So now, finally, you can see that we do get a different result, right? So what we have now is that the stress value is of 0.59, but the rank correlation is 0.91. Okay? So the difference that we have in these two, so we have a better result if we look at rank correlation, but we have a worse result if we look at stress value. And this results exactly from this difference on the focus of very different observations in comparison to, the overall arrangement that we have. So which one should you look at? Depends, right? It really depends on what you're doing. So how important it is to preserve distances as well for those points that are farther away from everybody else or not. So again, it really depends on the application that you're doing. Okay, but even though the result is visually different and even the overall fit that we get is also different, we can see that, of course, it will not be like completely different, right? They cannot be totally different from each other. So if we select, for example, some points in the edges, you'll see that they'll still be on the edges for the other method, right? So, I mean, you can play this at random and start selecting several points that are far from everybody else, right? Far from the other observations. And they will still be far from the other observations when you check against the classic metric. The difference is, of course, how far they are, right? So here you can see that these points are farther away from each other in comparison to what we have here. I mean, just by the looks of it, right? The scale is different, so I'm not really checking how much different they actually are. But anyway, visually, we can see that they look different. So the relative distances will be different, even though they are still overall in the same location in terms of how different they are from everybody else. All right. So let's move ahead and do the Manhattan distance, which we couldn't do before with the classic metric. So I'll change the distance function to Manhattan and then hit run again. So for names, I'll do SM. So first Markov and Manhattan. SM again. And okay. And now a much different representation, right? So let me try to put all three windows here. So what we have now is that stress value decreased again to something like 0.3-ish, right? It's 36 here. With the classic metric, it was 39. And this Markov with Euclidean distance, it was 59. But the rank correlations here is worse with the Manhattan distance. Right now we have 0.78 against 0.91 with the Euclidean distance and 0.80 with the classic metric, right? Again, if you select some of the points, roughly they'll have to be in similar locations, right? So the result is not absolutely different. It's just that with the Manhattan distance, you're actually summing up the differences that you get for each of the variables, of the 10 variables, and that is the length that you're considering for the distance between any two observations. This is what you are trying to preserve when you're doing this here in this two-dimensional space.
Yeah, the main difference between these two is the scale of the coordinate. As I showed you on the slide, the one goes from -3 to 6, and the other one goes from -2.3 to 2.7. So it's much more compressed relative to the squared criteria.
And again, we cannot really see how these, like what is the counterpart of this in the 10-dimensional space, but we can create one parallel coordinate plot, which will show us the 10 variables that we've selected, and roughly see what we are getting here. So I just hit this button here, right? The parallel plot, the parallel coordinate plot. And now I'll select the 10 variables. I'll double click them, and then they will be moved already to the right side. I hope I always get something wrong. Okay, last one. All right. So just double clicking, you can move all 10 variables to the right side. And then once we hit OK, we get the parallel coordinate plots. I mean, with all these variables and all these observations, it doesn't show that much. It's just a lot of lines, right, connected. But if we select in any of these, the scatter plots that we have, if we select any 2 points that are close to each other, so let me find, let's say this 2, you'll be able to see that roughly the values for each of the 10 variables between these 2 observations will be similar, right? Because again, they are very close to each other in this embedded space, in this reduced dimension space. And if we select 2 points that are far from each other, let's say these 2, it would be even better if I did it on the other direction, but anyway. See, so now you can see that the values or the attributes of these 2 observations, they vary much more, right? So you have that they are farther away from each other in terms of their variables as well, the differences that they have in their variables. Does it make sense? So how we're comparing these things? Yep. Okay, good. One final thing to talk about the MDS, I'll close this parallel coordinate plot. One final thing to talk about the MDS specifically, that is on the MDS tool here, is the category variable, right? So the category variable is pretty much for graphical representation. It will kind of get our overall result and then split it according to this the categorical variable, coloring it in different colors and showing on the map exactly, on the scatter plot, exactly who they are, right? So we can use these to compare different regions, as we'll do now, or it could be anything else, like if we had groups or racial profiles or income or whatever, right? We could use these categorical variables to see how these observations behave when categorized by it. So I'll just keep these I'll move this back to Euclidean, and I'll check this box. And we don't want to use IDD because this is the identification variable, right? So we would have a single category, like one single observation in each category. So let's choose red code. So red code is the code for the region. Differently from the representation that Luke has in the book, we do not have here the layer of the regions in Italy, right? We would need to dissolve the actual Italian representation and then have the region. So of course, we're not doing this. We don't have the shape files, but we can just run it anyway.
Yeah, the graphs in the book overlay feature. where you can put multiple values on the same map. And achieve.
Yeah. So here I'll just call it sreg, the new coordinates. And see, we have the same result that we had before for this Markov with Euclidean distance, but now it's categorized, right? So from here, we can see exactly how the points that belong to each category, how they are distributed in this abstract space. And then, of course, since it's as in this case, we're doing regions, we can check the actual geographic space and see like how they are represented, right? So here I'm choosing this region 4, and then you can see here on the map that it's selecting all these points and the neighbors, right? I probably still have the connectivity. Yeah, let me uncheck it. So now we only get the points. See? So now we have that all these points that belong to region 4, I don't know the name of this region in Italy, but you know, all these observations that are in this region, they are very close to each other, but some of them are very close in this reduced dimension space. Some of them are not. Some have very different values for their variables. And then, I mean, we can check any region in the map that we want to see. Oh, this is an interesting one, actually, right? Because it's, again, a region in Italy, so all the points are clustered in the geographical space, but in terms of variables, they are very far from each other. All right? Okay, so this was everything all the options that we had from the MDS window. So what we can do now is see the intersection between this geographic space, so actually see it more formally, the intersection between geographical space and the abstract space of the variables. So let me close this representation so we don't end up with too many windows. And then let's go back again to our weights manager. So in the weights manager, we already have the the 6 nearest neighbors geographic matrix. Let's create another 6 nearest neighbors, but now not taking into account the geographic location, but the coordinates for that we got from the MDS. So to see the neighborhood based on proximity in terms of the variables, right? How similar they are. So again, I'm selecting the ID variable, distance weight, k nearest neighbors, 6. And the difference will be here now. I don't want to use the coordinates, so the centroids. What we want to use is what we just created. So not the reg, I mean, it would be the same. But let's just select this V1S. So the first dimension that we got using this Markov method. And then for Y coordinate, we can use V2S. So the second dimension that we got when we considered the Markov transformation. Does it make sense to everyone? So basically, we are coming back to, no, this is Manhattan. Where was it? Here. We're coming back to this plot and creating a weights matrix that we'll check each of the points and find the 6 points that are closer to it. So the nearest 6, and say, okay, these are neighbors. Okay. Right, so I'll hit create. So now I'll call this MDS Markov. So now we have both matrices loaded. And as Luke said, since this is the one that is active now, if we go to our themeless map and we click on connectivity, show selection and neighbors, this is what we'll get, right? So if I select anyone like this, let me select it like this. So I get its 6 nearest neighbors. So they are not really neighbors in the geographic space, but here they are, right? So they are neighbors in the space, the abstract space of the variables. Since we now have 2 different matrices, we can select both from the Weights Manager window and then create the intersection between them. So basically, we will see how, like, where we have an overlap between the 6 nearest neighbors in geographic space and the 6 nearest neighbors in the abstract space. So intersection. Now give it another name. So let's do KNN6 versus MDS Smakoff. Save. Okay. Now we can get the connectivity graph from this new matrix, right? The intersection. And the graph will show exactly where we have the overlaps, right? As we did, I think, in our first class, we can change the colors of this connectivity, right? Like, let's change it to red, because then it highlights what we get. So these edges, they are showing to us, or they are highlighting the observations that are both close in geographical space and the space of variables, so local clusters, right? So we have similar values for the 10 variables. At the same time, we have a similarity of geographic location, okay? So this is what we get once we do this, when we do this intersection. One thing to notice, or to note actually, is if we roll back to the weights, the geographical weights, okay, and then 6, as Luke mentioned, here we have the percentage of non-zero. So it's basically how many combinations we have of neighbors once we selected 6 neighbors for each of the observations, right? So we have that 2.3% of our data is connected, of our observations is connected. If we check the intersection now that we have between KNN6 and the MDS's Markov, this number will, of course, be less than 2.3, or at least as the maximum will be 2.3 if we have a full overlap, right? But in this case, what we get is 0.16. So if we divide the 0.16 by the 2.3, we have the percentage comparison, right? We can see how many, or what is the percentage of the links that we have geographically, what is the percentage of them that are also links that we have when we look at the variables, all right? So we'll do that later. The last thing we'll do, I have already prepared a spreadsheet for us to use to compare everything that we get. Okay, I had already also prepared to do a local neighbor match, which is pretty much what we did, right, test, but with the p-value and the HDB scan on these 2 dimensions. But I'll skip them for now. If we have time in the end, I'll come back. I'm just worried a little bit about time. And of course, we want to do tSNE, right? So these are more a spatial analysis that we can do with this, right? To see the cluster concentration by using HDB scan, and to see actually what, to give like a more formal approach to this intersection between the weights and check the p-values that you get from these matches. But again, let's skip it for now. I hope we get time to come back to them later. But for now, let me close all these things. So let's close everything that is MDS. Let's just keep this the themless map. And let's go to clusters again. And now select tSNE. So let's look at the stochastic neighbors. And as Luke explained earlier, the difference is that now instead of checking how different the distances are between the points in the high dimensional space and the embedded space or the reduced dimension space, instead of looking at these distances, the differences that we get in the distances, what we will look now is to the probability of being neighbors, right? So we change from the concept of distance and then neighborhood defined by distance to the concept of probability of being in the neighborhood of one and the other one. So if we look at the window that we get from this tSNE tool, it's roughly divided in 4 parts, right? So in the top right, we have this where the scatter plot will be plotted. So it's this visualization window, right? So we'll see the scatter plots that we get for the 2 dimensions. In the top left, we have our variables. So we'll select the same 10 variables. Bottom left, we have several parameters. Luke explained them all. I'll just go over them very briefly again, just so you remember exactly what they mean. And then bottom right, we have a window that will show us the summary for the iterations, right? The error and the iterations where we are at. So let's begin by selecting our variables again. So kpret 13, Z13, liquid asset 13, NPL, LLB, intra, depot, EQLN, XP, sir. Oh no. And the last one, my hold on comment was lost, so I lost everything. I'll do it again. It had to happen in the very last one. Yep.
Well,
Oops, thank you again. Sir. Okay, finally. Yes, I'll just get it out of that window so I don't risk touching it again. All right, so we've just selected the 10 variables. Let's begin by just running the defaults, and then we can come back and, change some of these parameters and see what happens. But before we start, let's decrease the speed. Otherwise, it will be just too fast and it will be done and we won't see anything. So let's put it very slow. I mean, you'll see that it will be too slow by far, but then we can change it while it's moving, right? So at least we have time to change it while it's moving already. Okay, now let me decrease the window size so I can find the run button. There it is. And hit run. Oh, by decreasing the window size, I lost the speed. Okay, Zoom does not allow me to go further. Anyway, here. Right, so as you can see, it's changing a lot, right? From one iteration to the other one, because basically at the beginning of the iteration, the results are very different because it hasn't learned enough, right? So it's not really taking into account much of what it's got. So it's improving a lot from the beginning and changing a lot. And then, as Luke said, at some point, it just gets more stabilized, right?
I think you had some observations selected, so.
Oh, sorry. We can go back. No, I'll hit just stop and then run again. Yep. Oh, okay. Sorry. So see, so we get these very different results at the beginning, but then it's as it learns on each of the iterations, then at some point it will become more stabilized until it converges in the end or it goes through all the iterations. So what we have in this summary here is that for every 50 iterations, we get what is the error, right? So you can see that the error is diminishing every time. And then at some point, let me increase the speed.
You see the dramatic change, right? From in the 50s to 0.9.
Yeah, so when it went from this to that, probably it's when it stabilized and then it stopped changing. And then see, it's already changing the error only in the third decimal. So, I mean, you can see that it's not gaining much until it will finish the iterations all the way to the 5,000 that we selected, right? So basically, in the end, it was not changing at all, or at least, yeah, it wasn't changing at all the value of the error.
One thing, it's kind of a double thing that may be confusing, is that we cheat a little bit. And when we compute the stress value in the iterations, we make some shortcuts. So the final cost is close, but not exactly the final error at the final iteration. Even though it should be the same, because it's the same solution, nothing changes after the final iteration. But the final cost is the complete calculation, whereas what you get at the iterations is based on sampling. So that it doesn't take too long to compute it each time. Because we have to compute these distances for every pair. And that, you know, I mean, for the Italian data, it's reasonable, but for bigger data sets, that's in the order of a square, so that's very large.
Okay. So what the tSNE was optimizing is this final cost, right? To get it as minimal as possible. The intuition behind this final cost is roughly the same thing that we were doing in the MDS, in the sense that you're checking how much you could preserve the distances, but they are not comparable at all, because here we're focusing on local distances, right? Once we have what is the perplexity that we're considering here, it's basically how narrow is our focus, right? So if we have a small perplexity, it means that our focus is very narrowed down to the local observations. So the cost will reflect that we're looking at a very narrowed area. Whereas in the MDS, the stress indicator, which was the one that was being optimized and minimized, that had nothing to do with local variables, with local observations, right? It was a global measure of the discrepancies that we had in the distances. So that's why we cannot compare, even though the two methods are roughly doing the same thing, trying to decrease the dimensionality of the data while still preserving the relative differences that we have in our observations. Okay, so here we can save this result. Then I'll do tSNE for name, tSNE, and hit OK. I shouldn't have closed the last MDS representation. So if you closed it as well, let's just run it again. So clusters, MDS. Oh my God. I think I'll leave this window open forever with the variable selected. Let's go through 12. All of them again. Just because even though we cannot compare the value of the stress against the value of the final cost, we can compare the value that we get for the rank correlations, right? Because then that is a comparable measure. It's not about the optimization like that we're running. It's not that. So I'll do smack off again. Okay, run. So V1 S, V2 S. Okay, good. So here we have again this MACOF, and now we can check it against the tSNE. So again, the visualization is quite different, right? The distribution of the points. We cannot compare stress value against final cost, but we can compare rank correlation with rank correlation, right? One thing to note is that, again, we're using tSNE because we want to give a stronger focus on the local observations, right? Or the local proximity. So the observations that are closer to each other. Therefore, rank correlation is a measure that we can use for comparison, but keep in mind that although it's a good indicator for the quality of fit of the MDS, it's not that good an indicator for the quality of fit of the tSNE. And the reason for this is that for the tSNE, we are focusing again on local discrepancies, whereas the rank correlation is a global measure of discrepancies, right? So that's why it will tend to be poorer in the rank correlation, because again, it's focusing on the local similarity, okay? So from this, we can see how in the tSNE, the decrease in the dimensionality preserved the distances in a worse way, right? Because the rank correlation is smaller. But we know from the method that the distances for the units that are closer to each other, those distances will be better preserved in the tSNE in comparison to the MDS. Okay, so again, it's all about the focus that you want to give and what you want to do. Going back to the tSNE window here. So for the parameters, I've just mentioned again perplexity, as Luke explained it early. So perplexity is all about the neighborhood. So how narrow is the focus that you're doing for what you're calling local. So by doing 30, we're saying local is very important to us. If we change this to 50, and that's what we're going to do, we're saying, well, we want something more balanced between local and global. And if we change this to 100 or like more than 100, we would be saying, no, local is not that important, so global is all that really matters. And then I would ask, so why are you doing tSNE, right? It wouldn't make sense to do something like that. You could just do a PCA or MDS, and then you would have a similar result, right? So if you're doing tSNE, it's because you want to give a greater weight to the local neighborhood. So perplexity should be, I would say, something around 50 or whatever, 30, which is the default, which is very local. But then since you're very focusing on a very local, you have a very local perspective, the trade-off, as Luke mentioned, is the cost, right? So the cost will tend to be greater if you're doing so. So let's check if that is true. Let's change perplexity to 50. Everything else the same. Hit run. So we have here the result, and then we can compare. I mean, we're seeing that already, right? I don't think there's any need to say. So if you compare them, like we have a very similar representation, right? So by increasing the perplexity a little bit, it did not change the result that much. But yeah, I'll also save, otherwise we don't get the statistics, right? So let's do save. V1, P50, V2, P50. So see, rank correlation now is slightly increased because we get a better result since we are moving towards this more global focus on our variables. But we didn't go too far, so we didn't get too much rank correlation, increasing rank correlation, but still we can see like what we get as a representation. Okay, for perplexity. Okay, let me finish, close this. Now we can change. Again, I'm just worried a little bit with time. So I'll just talk about theta and not change it. So the theta is the criterion that determines how much we want to simplify our embedded space, the probabilities for the embedded space in our simulations. So as Luke said in the first part of this class, P will always be the same, right? Because it's what we observe. But Q are the probabilities that will be changed according to the iterations and the simulations that we're running. So if we simplify it by like a lot, of course, we will do faster, but we tend to do worse, right? And if we set it to 0, and in this case, we have a very small data set, so we could set it to 0, we wouldn't have any simplification. So we would actually get that the final cost here would be pretty much, I think it would be the same, right, as the last iteration, because, yeah. So it's a very small, so it won't change much, right? So that's why let's not run this. But anyway, so this is what theta is for. So if you have a very large data set, you want to keep theta something greater than 0. If you have a very small data set, you could just set it to 0 and that's it. The learning rate, again, I won't change this because I don't think there is any example changing it in the book as well. But the learning rate is basically, Luke showed it again when he was showing the equations, but it's basically how much difference you will have from one in the iterations, right? So how much you'll learn from one iteration to the other. So how different the steps that you'll take. And for the momentum, what we have here is that we have 3 options for momentum, right? So the first option that we have here for momentum is the starting momentum. Then we have the final momentum, and you see that it's going to increase once we change the iterations. And then we have the number of iterations to switch from one momentum to the other, and it's set to 250. So the idea here is that once you move forward with the iterations, you have already learned a lot, right? So the data is already kind of getting more stabilized. So you're kind of already converging to something. So you can increase the momentum, so you can like allow for a greater shift between everything, right? So you can try to avoid any local optimum that you may have fall into during the first steps of the iterations. Right, Luke? Did I say it right?
Yeah, it's how much you allow the adjustment to happen. So typically, and this is again, depends on each example. You start with a lowish value, and then after you've done enough iterations, you can crank it up. And it automatically sets it at 250. We got these defaults from the literature. We don't really know what are good values, but typically what you would do if you can is to experiment with some of these combinations and see how much it matters.
Okay. So that's the thing. So with the momentum, with high value of momentum, you have less smoothing, but then you risk more overshooting, right? So that is why you change the momentum in between the analysis. Okay, so we already have the first one saved. Let's just keep it. And now let's check the result that we get from this tSNE against geographic space one more time, right? So I'll close this. And let's go back to our weights manager. I can't find it here. Yep. And creating yet another weights matrix. So I'll hit create again from the weights manager. Select ID variable, IDD, distance weight. For X coordinate, I'll choose the V1 tSNE. For Y coordinate, I'll choose V2 tSNE. K nearest neighbors, and 6 one more time. Okay? And then hit create. So now we have K and then 6, but tSNE. So I won't show it to you again in conscious of time, but let's already do the intersection. So I'll select it and select KNN6. Can I increase these so you can see both selected? No, not really. But anyway, so I'm selecting this result from the tSNE with the geographic neighbors and then intersection. And now, KNN versus tSNE. Save. Okay. So now we get a percentage of non-zero of 0.2, right? So basically, we can use this neighbor again to see the connectivity graph, and it will show us, highlight them, color, red. It will show us again the overlap that we have between proximity in geographic space, proximity in the space of variables. And now, if we want to compare and see how much these overlaps compare between the methods that we used, we can just use this percent of non-zero value and compare against them. So I prepared this. We didn't run all. I mean, I don't think I have all the combinations open still, but anyway, I think I closed only the MDS. So we'll just skip it. So the first thing we need to do if you want to compare them is to note what we have for percentage of non-zeros in our base geographic weights matrix, right? So here we have a 2.3%. So we can just come here and type down 2.3. MDS, I did not save it, or we did not create a weights matrix. So let's just skip it. Let's go straight to MDS Smakoff. Here. So for the MDS is Markov, the intersection with KNN6, we have 0.16. And then finally, for the tSNE, the intersection again, we have 0.2. So if we divide this by what we get in our basic, geographic, and then we can actually do percentage. Okay. We can compare these two, right? And see that, as we would expect, with the tSNE, since the focus is more on local proximity, we do get a greater common coverage percentage, because again, we're focused on the local neighbors, we're focusing more on local neighbors than what we got from this Markov. So if our objective is to do any geographical analysis or actually spatial data analysis on these, reducing these methods to reduce high dimensionality, the tSNE, as Luke said, would be a better tool for us to do this because of the focus it has on the local observations. All right, I think this is it. Anything else, Luke?
Well, I could keep going.
Oh, yeah. All right, so let me stop this here.